Complex numbers. Theorem on nth roots. What are they? Complex numbers are a mixture of a real number and an imaginary number. Why? Helps in the design process of jet engines. Interesting fact, the light tan-colored Florida panther is one of over 30 subspecies of cougar, or the species name Puma concolor, found in North America. Now, let's take a look at the equations that are important with complex numbers. We have the standard complex form and the trigonometric form of a complex number, and how to convert between the two. Now, let's take a look at z is equal to r times the quantity of cosine theta plus I sine theta. Using de Moivre's theorem, when we multiply the same complex numbers, we have the modulus raised to a power, and the argument multiplied by that same power. What do you think happens when we divide by the same complex number? Well, what are the inverses of a power raised to the n and multiplication? That's right, the nth root and division. Before we put the nth root in action, let's talk about the square root of 16. What is the square root of 16? That's right, 4. But 16 has two numbers that are square roots. The equation that would give us the square roots is x squared is equal to square root of 16. So x is equal to plus or minus 4. But the principal root, or the main root, is 4. Let's take a quick look at a random number, 3 plus 3i. The first argument we find is pi over 4. But that is not the only argument we could use. We could keep going by adding 2 pi. So what do you think is the next one? That's right, 9 pi over 4. And the one after that is 17 pi over 4. And so on and so forth. However, pi over 4 is the principal argument, or the main argument. What about x cubed is equal to 1? How many cube roots do we have? We know there's only one main root in the real world, but in the complex world, we have more. Let's find out by taking a look at the example we're going to discuss in today's video. Let's take a look at the steps. Step 1, draw. Step 2, use the formulas. Step 3, follow order of operations. Now, let's read the question. Find the cube roots of 1. Let's write down the equation we need to solve. So z cubed is equal to 1. Let's subtract 1 on both sides. So we have z cubed minus 1 is equal to 0. Since we have a difference of cubes, we can factor it. So we have a quantity of z minus 1 times the quantity of z squared plus z plus 1 is equal to 0, which means our first root is 1. Now, to find the complex roots, we use z squared plus z plus 1. Let's use the Pythagorean theorem to find them. So we have z is equal to negative 1 plus or minus the square root of 1 squared minus 4 times 1 times 1, all over 2 times 1. Let's multiply the numbers. So we have z is equal to negative 1 plus or minus the square root of 1 minus 4 over 2. And the square root of 1 minus 3 is the square root of 3i. So we found our two complex roots, negative 1 plus or minus the square root of 3i over 2. Now let's graph the roots. Here we have z sub 1, which is 1, z sub 2, which is negative half plus square root of 3 halves I, and z sub 3, which is negative half minus square root of 3 halves I. We know the modulus of z sub 1, which is 1. What do you think is the modulus of z sub 2 and z sub 3? Let's find out. Let's calculate the modulus of z sub 2. So we have r sub 2 is equal to the square root of negative half squared plus the square root of 3 halves squared. And negative half squared is 1/4, and square root of 3 halves squared is 3/4. So we have the square root of 1/4 plus 3/4, which is square root of 1, and the square root of 1 is 1. So the modulus of z sub 2 is 1, which means z sub 3 is as well. What do you think would happen if we were to draw a circle with radius 1 on the graph? All 3 points would be on the circumference. Now let's find the argument. Once again, let's use z sub 2. So cosine theta sub 2 is equal to negative half, and sine theta sub 2 is equal to square root of 3 halves. What do you think is the argument, or theta sub 2? That's right, 2 pi over 3. And if we do that with z sub 3, we get negative 2 pi over 3. But the distance is 2 pi over 3. And what do you think is the last section? That's right, 2 pi over 3. Because 2 pi over 3 plus 2 pi over 3 plus 2 pi over 3 is 6 pi over 3, or 2 pi, or a complete circle. All that is to say that c sub 1, c sub 2, and c sub 3 are equidistant on the circumference. Now we know the cube roots of 1 and the angle in between them. Let's find them another way by using sine and cosine. Instead of moving 1 to the left side and factoring, we're going to rewrite 1 as a complex number using cosine and sine. We know the modulus of 1 is 1. But what do you think is the argument? That's right, 0, because 1 is on the x-axis. Now that we have rewritten 1 as 1 times the quantity of cosine of 0 plus I sine of 0, let's bring back de Moivre's theorem, which is z to the n is equal to r to the n times the quantity of cosine of n theta plus I sine of n theta. We've already changed the right side, so let's bring it down. Now, let's change the left side using de Moivre's theorem. So z to the 3 is equal to r to the 3 times the quantity of cosine of 3 theta plus I sine of 3 theta. So we can say r is equal to 1 because 1 to any power is 1. And cosine of 3 theta plus I sine of 3 theta is equal to cosine of 0 plus I sine of 0. We found one real solution. R is equal to 1. Now, let's take a look at the complex solutions. We can separate that into two equations. The first equation, cosine of 3 theta, is equal to cosine of 0, deals with the real numbers. And the second equation, sine of 3 theta, is equal to sine of 0, deals with the complex numbers. Let's start with sine of 3 theta is equal to sine of 0. Since we have sine of something is equal to sine of something, we can say 3 theta is equal to 0. But that's not the only solution. What does sine look like? Well, let's graph it. Since sine is a sinusoidal function, it goes up and down forever and ever, so we have infinitely many solutions. But where are those solutions? Since sine of 0 is 0, our solutions are where the graph crosses the x-axis. We know 1 is 0, and going in the positive direction, what do you think is the next solution? That's right, pi. The next one? That's right, 2 pi. And the next one? That's right, 3 pi. And so on and so forth. To denote that, we write plus k pi, where k is an element of the set of integers. Let's drop the 0, so we have 3 theta is equal to k pi. Let's divide both sides by 3, so theta is equal to k pi over 3. Now, let's solve cosine of 3 theta is equal to cosine of 0. Since we have cosine of something is equal to cosine of something, we can say 3 theta is equal to 0. But that's not the only solution. What does cosine look like? Well, let's graph it. Since cosine is a sinusoidal function, it goes up and down forever and ever. So we have infinitely many solutions. But where are the solutions? Since cosine of 0 is 1, our solutions are where the output is 1. We know 1 is 0, and going in the positive direction, what do you think is the next one? That's right, 2 pi. And the next one? That's right, 4 pi. And the next one? That's right, 6 pi. And so on and so forth. To denote that, we write plus 2k pi, where k is an element of the set of integers. Let's drop the 0, so we have 3 theta is equal to 2k pi. Let's divide both sides by 3, so theta is equal to 2k pi over 3. Now we need theta to satisfy both equations. But not all solutions of sine are viable. Exactly half of them do not work. Only the even multiples of pi satisfy both equations. Let's show that by drawing lines from the top of the sine graph to the bottom of the cosine graph through the solutions. The lines only cross the even multiples of pi, which means theta is equal to 2k pi over 3 is what we work with. That is a general solution for the argument. Now, that makes sense, because that is the distance between each point on the circumference. Knowing that we have to work with cosine, we can generalize the nth root formula. So we have the nth root of z is equal to the nth root of r times the quantity of cosine of theta plus 2 pi k over n plus I sine of theta plus 2 pi k over n, or if you prefer, 360 degrees instead of 2 pi. Let's put those formulas into action. Let's find the first cube root by substituting 0 for k and 1 for r. And the cube root of 1 is 1, and 2 times 0 times pi is 0, and 0 plus 0 over 3 is 0, and cosine of 0 is 1, and sine of 0 is 0. So we have 1 times the quantity of 1 plus I0, and the result of that is 1. And that is our first complex number. Let's move on to when k is 1. Let's find the second cube root by substituting 1 for k and 1 for r. And the cube root of 1 is 1, and 2 times 1 times pi is 2 pi. And 0 plus 2 pi is 2 pi. And cosine of 2 pi over 3 is negative half. And sine of 2 pi over 3 is square root of 3 halves. So we have 1 times the quantity of negative half plus I square root of 3 halves. And the result of that is negative half plus square root of 3 halves I. And that is the second complex number. Let's move on to when k is 2. Let's find the third cube root by substituting 2 for k and 1 for r. And the cube root of 1 is 1. And 2 times 2 times pi is 4 pi. And 0 plus 4 pi is 4 pi. And cosine of 4 pi over 3 is negative half. And sine of 4 pi over 3 is negative square root of 3 halves. So we have 1 times the quantity of negative half plus I negative square root of 3 halves. And the result of that is negative half minus square root of 3 halves I. And that is the third cube root. Now it is your turn, so go ahead and pause the video here so you can take your time to answer this question, and I'll show you the result in 3, 2, and 1. Did you get it correct? Fantastic. If not, there's always tomorrow.